We're talking about distributions right now. And what a distribution is, remember, is a rule that maps from a function to a real number, as opposed to a function which maps from a real number to a real number. It's a rule that maps a function to a real number. Here was one example of such a distribution. Here's the distribution, and here is the rule. You'll see that once you integrate the t out of it, you get a number. So we went from a function to a number. This guy is called a regular distribution because this f inside the integrand is a regular, legitimate function, and this is all normal calculus. What about an irregular distribution? Like this guy, the delta distribution. What it does is, well, the rule is the number it maps to is the test function evaluated at an argument of 0. That's the rule. If you think about it, that is the sifting property right there. So this guy actually is like the Dirac Delta function, but it's a legitimate distribution in this case. We could write it this way, but this is really an abuse of notation because this guy here is not really a function. This actually doesn't have meaning because this guy isn't a function. All it means is you go from here to there. We could write right there. This integral kind of doesn't really mean anything. Because this isn't a function in pure distribution theory. But anyway, so this Dirac distribution now is defined by the sifting property. It's not something derived from axioms or other properties. It defines it. And here's what bugs me about distribution theory. The severe, I call it severe restrictions on the test function. It must be infinitely differentiable and have compact support, which means it's non-zero over only a finite interval of the real line. Can't just decay like a decaying exponential. It can't just be 1 everywhere. It can't just be 1 over a pulse like that with sharp edges. It can't be a triangular pulse because it's not differentiable at the peak of the pulse. I found it hard to even contrive a function that satisfies those requirements imposed by distribution theory. Not t, not a polynomial, not science and cosines. Here is an example, and it had to be contrived. And the big thing we want to use the Dirac Delta function with, or the distribution, is to do this sifting. But you got to sift a function, but hardly any functions satisfy the requirements. So how do textbooks and other people deal with it? It seems to me like they largely ignore the issue. That, or we kind of do this thing. We say, well, we're really only interested about things at the impulse in that neighborhood. So we'll assume we could kind of take the function we want to use and know that we can kind of truncate it somehow to obey all the rules of distribution theory. They said Paul Dirac's approach was too sloppy. To me, this is a different kind of sloppiness. Anyway, that's as deep as I'm going to dive on distribution theory. I'll talk about this third approach in another video.